Hi folks, in this video we are going to solve 4 problems, all of them using the equation PV is equal to nRT. In other words, we are talking about ideal gases. So here's the first problem. 4 processes are given and you're asked to describe in words what each one represents. Let me start with the third one. We are told that this is an isotherm. So this is an isotherm. What does that mean? It means the temperature is constant. So if you look at our equation of state, PV is equal to nRT. So temperature is constant, number of moles is constant. R of course is 8.3 in SI units. So the right hand side is constant. So the pressure is constant divided by volume, which means the pressure is inversely proportional to the volume. Which means when I double the volume, the pressure becomes half. So if you look at this, if I go from a certain volume V1 to double V1, 2V1, the pressure will drop from P1 to half P1. When the volume triples, the pressure becomes 1/3. Now if you look at this curve, you can see that as the volume V goes to infinity, the pressure drops to 0. And likewise, when the volume goes to 0, the pressure goes to infinity. So I've drawn a part of this curve. This curve has a fancy name, rectangular hyperbola. You don't have to know the name. It is just a graph y versus x, where y is inversely proportional to x. Now I have drawn this graph for a certain value of temperature, T1. What if I change the temperature to T2? The constant C is different. I plot the graph again and it will come out something like this, similar in shape but slightly higher. I plot this for another temperature T3, I might get a graph something like this. Question is, which is the higher temperature, which is the lower temperature? That's very easy to find out. Pick some value of the volume and see, as I go up from the curve T3 to T1 to T2, the pressure is increasing with fixed volume. As I raise the temperature, the pressure goes up. So therefore, you can see that T2 is greater than T1 and that is greater than T3. So these curves are all called isotherms. Now how do we achieve an isothermal process? Here I have n moles of the gas in an airtight cylinder with a freely moving piston which can slide up and down without friction. And we have some sand on top of it so that the weight of the sand plus the piston is equal to the pressure of the gas multiplied by the cross-section area. That is, the pressure multiplied by the area is the output force exerted by the gas, which balances the weight of the sand and the piston. Now, what I want to do here is increase the volume at constant temperature. Can you see that? How do I keep the temperature constant? So the first thing we do is we put this cylinder in contact with a heat reservoir and we represent the heat reservoir by just a rectangle. But what is a heat reservoir? A heat reservoir is an object with a large heat capacity. I'll explain that. For example, a lake. If I add some heat to the lake or remove some heat, the temperature of the lake changes by a negligible amount. Its temperature is practically constant. So the heat reservoir can be a lake. I can put this cylinder partly submerged in a lake. But do I need to find a lake? Not really. A bathtub will also do the job. And if the apparatus is small, maybe even a bucket of water will do the job. So what is a heat reservoir? A heat reservoir is an object with a large heat capacity. What is heat capacity? Heat capacity is the amount of heat required to raise the temperature of the object by 1 Kelvin. A large heat capacity means to raise it by even 1 Kelvin, I need to supply a large amount of heat. So these ordinary changes where some amount of heat flows into it or flows out of it will produce negligible change in the temperature. Since this cylinder and gas are in contact with this reservoir, they will be at the same temperature as the reservoir. So if this temperature is T1, we can assume the gas stays at temperature T1 as I slowly remove the sand little by little. As I remove the sand little by little, the piston will move up, the gas will expand at constant temperature, and the process is represented by this graph. So this is an example of an isothermal expansion. During this isothermal expansion, two things are happening. Now, as the gas pushes up on the piston and the sand, the gas is doing work. Now, the gas does work, it loses energy. Now, we'll see later that the internal energy of the gas, of an ideal gas, is proportional to the temperature. So, if it only did work, it would cool down. The temperature would decrease. But in order to keep the temperature constant, heat would have to flow in from the reservoir. So, during this isothermal expansion, the gas is doing work and heat is flowing into the gas. Let's look at the first process. You can see here that the volume is increasing at constant pressure. So this is called an isobaric process, a constant pressure process. In fact, this is an isobaric expansion since the volume is increasing. Now, if I want to keep the pressure constant, I don't change the amount of sand. So the weight of the sand and the piston remains constant. Since that is balanced by the pressure multiplied by the cross-section area, the pressure is constant. But I want the gas to expand. So how do I let the gas expand without touching the sand? I heat it gently. So during this isobaric expansion, two things are happening. Heat is flowing into the gas, and furthermore, the gas is doing work by lifting up the sand and the piston. And notice one more thing in this process. Here, at constant pressure, the volume increases. So if you look at our equation, PV is equal to nRT, the pressure is constant. If the volume is increasing, the temperature is increasing. And that can be seen easily because if I draw a few isotherms, you can see that our process cuts across several isotherms, going from a lower temperature isotherm to higher one to an even higher one. So the temperature is increasing. Let's go to the next one. Here, at constant volume, the pressure increases. How do we do that? One way to keep the volume constant is to clamp it down so that the piston can't move. But if I did that, how do I know that the pressure is increasing? Because I can see what the pressure is by the weight of the sand and the piston. So we do not clamp it. I control the pressure by controlling the amount of sand. So what I want here is the pressure to increase while the volume stays constant. So one way to do it is start adding sand little by little so that the pressure increases. What will happen? The piston will start moving down, but then you start heating it gently, which counters the effect of the increased sand. So I keep adding sand and I keep heating it gently. So what happens? Two things happen. As I keep adding sand, the volume remains constant. So no work is done even though the gas is exerting more and more of a pressure. Pressure is increasing, but there's no displacement. So the force exerted by the gas does no work. At the same time, some heat goes into the system. So as the pressure increases, the temperature increases. So the gas is not doing any work, so it's not losing any energy. At the same time, heat is flowing into it, so its internal energy increases, so its temperature increases. And that can be seen right here when you realize that this line, our process, goes right across several isotherms. In fact, as I go up, it goes from lower to higher temperatures as the pressure increases. And now we come to our fourth graph. Let's label the points. This is point 1. So this represents P1, V1, and that's the state of the gas, let's say initially. We now expand it at constant pressure. It's an isobaric process, bringing it to state 2. And here, if the pressure is P1, V1, pressure is P1, volume is V1. At this point, at point 2, the pressure is the same, P1, but the volume is V2. And then we take it through a constant volume process, but now the pressure is decreasing. Now, how do we do that at constant volume with the pressure decreasing? So one way to do it is to start cooling it, and as the piston tries to come down, remove sand so that the pressure decreases, but the volume remains the same. So this is an isochoric process, a constant volume process. We bring it down to a point where the pressure is P2. This is the lower pressure. P2 is clearly lower than P1, and the volume is still V2. And from P2, V2, we bring it back to P1, V1 along an isothermal compression. Since the temperature is constant, P2, V2 is equal to P1 V1. In fact, every point along an isotherm represents a constant temperature point. So at every point along an isotherm, the product PV is the same. So when I go from P2 V2 to P1 V1 along an isothermal process, P2 V2 is equal to P1 V1. Now I've come back to the starting state. So this is called a cyclical process. During a cyclical process, you come back to the starting state, and that means the pressure, volume, temperature, everything has come back to its original value. The internal energy of the gas has come back to its original value. Later on, in a future video, we will see that during this cyclic process, the work done will turn out to be the area enclosed by this curve, provided we move clockwise as we did in this problem. If we moved anti-clockwise, the work done by the gas will turn out to be minus of the area. We'll talk about that in another video. That's it for today, folks. See you in the next video. Bye-bye.